Magic numbers in nuclear physics are specific counts of protons or neutrons that make a nucleus especially stable. Examples are 2, 8, 20, 28, 50, 82, and 126. Think of a nucleus like a set of neatly stacked toy blocks where protons and neutrons fill up energy levels. When a level is completely full at one of those special counts, the nucleus is much harder to break apart, so it becomes extra stable. Each proton or neutron sits in a kind of orbital with different energies, and when all the lower energy orbitals are filled, the next particle would have to go into a higher energy spot, which costs more energy and makes the nucleus more tightly bound. That is why atoms with magic numbers of protons or neutrons tend to have higher binding energy per particle, lower likelihood to undergo radioactive decay, and sometimes show up as particularly common or long-lived isotopes. Scientists figured this out by measuring patterns of binding energies and observing sudden jumps or gaps that match those special counts. A common mistake is thinking magic numbers mean a nucleus cannot change or decay at all, which is not true because even magic nuclei can undergo certain decay modes under the right conditions, so do not assume absolute stability. Another misconception is believing magic numbers are fixed for all nuclei under all conditions. In exotic, very neutron-rich or proton-rich nuclei, the shell structure can shift and the traditional magic numbers may change. So researchers test extremes to see when that happens. Also, people sometimes confuse electron shell stability with nuclear magic numbers, but electrons and nuclear particles occupy entirely different shells and rules, so keep those ideas separate. For more short videos and materials about magic numbers and nuclear structure, visit www.gumballdegree.com.